So I have a rod, right? It's connected to some corner, or I would say some wall, might not even be a corner. From one side and from the other side is held by two cables, two ropes, I would say. It's part of some system. Honestly, I don't even know what is the whole structure, but it's taken out from a whole system. Now, the problem says, well, the problem statement says rod AB, which is rod AB, is is subjected to the 200 Newton force. It's connected to wall at point A, and then some force, 200 Newton force applied to this at point C downward. You see it on that. All right. It says find the reactions. Find the reactions at the ball and socket joint. Ball and socket joint A. So we are told what kind of joint do we have at point A, right? Point A is connected. There is some support, and now we know it's a ball and socket joint. Joint A, and the tension in cables or the BD and BE. One more piece of information we're given is that the color at C is fixed to the rod. So you don't need to be worried about color C. This is color C there, right? You don't need to be worried about that sliding on the rod. So it's fixed there. So we have a rod. We know it's 200, the force 200 newtons is applied to it downward. Might be the weight of, oh, it's not exactly the weight of the rod. And in this case, we can neglect the weight because we have not given any information about the weight. It would have been much better if the problem statement would have said that directly, that there is no weight, or we can neglect the weight. Okay, so we have that bar at point C. We can think about C as a point of color since it's fixed to the rod. 200 newtons downward, we have two cables, BD and BE, pulling it or holding this by pulling it in two different directions. And at point A, this rod is connected to some other part of this big system using a ball and socket joint. So, as I said before, multiple times, first thing we do, free body diagram. Right? Let's just draw the free body diagram for this rod. I'm isolating this rod. There is no other part in this system that I would probably be interested in drawing its for free body diagram. So there's no question of, oh, which part I should choose to draw the free body diagram. You can just go with the rod directly, since obviously it's the only thing that you can possibly use to find your unknowns. At least it seems like that. Start from there and see how things go. Let me try to draw that rod. I'm just going to cheat and draw it as a very thick line. Let's do it this way. There you go. We have our coordinate system. And, let's take this as x. If this is x, this would be y. And I'll take this as z. See where the coordinate system is, and all the way in the corner. And z-axis passes through point A. All right, so actually, you know what? I'm gonna have an easier time since I'm not given the axis here. Let's just choose it somewhere else. Let's choose it and let's put them here where we have the most unknowns. These are some tricks of the trade you're gonna learn the more problems you solve, you realize that it's actually easier to put the coordinate system where you have the either the most known values or most unknown values. In this case, I'm going to put it where I have the most unknown values, which are the support forces in that point A. So this is going to be the X, it's going to be the Y, it's going to be Z. Now, if you chose coordinate system anywhere else, you would have gotten the same, you're going to get the same results as we will get solving this problem, but your life would have been, depending on where you choose, well, I guess A is the best point. So your life would have been a little harder. All right, so let's put the forces on this one, now that we have our coordinate system. I'm going to put the force at C here. Let's call this, we actually have the value for that. You don't even need to put any name on this. So it's 200 newtons. I have cables. All right, so I have BD. Well, obviously, there's only one way that the cable can have a force, and it's under tension. So I'll put it this way and this way. Let's call this TD and call this TE. This is what I did. And this is point B. And this is point A. What else do I have here? Any other force that I have to take into account when I'm isolating this bar, this rod from its whatever environment it has? Exactly. I didn't put the main set of forces. Exactly, ball and socket reaction forces, which, if you remember from those supports we introduced, and if you don't remember, take a look at it. You can always, whenever you remove a ball and socket joint, I think the previous example we did also had a ball and socket joint, so hopefully that's more fresh in your mind, that when we remove a ball and socket joint, we basically put just three forces in three directions in Cartesian coordinates. All right, so I'll do the same here. Let's put this and this and this. So the thing's less confusing, I'm going to remove this A. Since we know that's point A, I'll call this A Z, A Y, and A X. Since I don't know the value, as we said when we draw a free body diagram, we put the known values, and whatever unknown value we have, we just use some notations to represent that value for force or moment or everything. And that's pretty much it. Since the ball and socket joint does not have any, does not prevent the system from any kind of rotation, so we're not going to have any moment as the reaction. All right. So far so good, right? We have the forces, we have our free body diagram. All we need to do is to form those equations of equilibrium, right? All summation of all the forces should be zero in three directions, x, y, z, and summation of all the moments should be zero. Let's do that. I will define, I'm just going to be consistent with what I did last time. So I'll define the force at point A with the three components. So I'm going to define FA. Remember, before I do this, remember, we are forming those equations. And we said the first step to form those equations, you're probably sick of hearing me saying that is to represent the forces in Cartesian coordinates. So that's what we're going to do. I'm going to say force at point A would be AX, obviously, in I direction, plus AY in J direction, plus AZ in K direction. All right, that's A. Easy to represent in Cartesian coordinates since I just took those three forces as support forces along those axes. How about other forces? How about TE? Let's represent TE in. So that would be the magnitude of TE. What is the direction of TE? You know, without even using any points along any specific direction. Looking at the x, y, z coordinate I put there, plus x, exactly. Thank you, guys. So it's going to be I. So TE, whatever the magnitude, times I vector. It's along x-axis. Here is TE. Don't get lost where we get TE. Just the tension force applied to this end of the rod from cable BE. TD, same story. The magnitude of TD, if you look closely, you will see that it's along positive Y. So just put J. Whatever is the magnitude, multiply the direction. And last but not the least is the force applied at color C. Right? And that force is downward, so it's along Z-axis, and it's negative as a result since it's downward, since we took Z positive upward. So that would be FD. I'll just call it FD. Minus 200 in K direction. Let me put FD here. So if you're following the free-body diagram, don't get lost. All right. Without any complication, I just got my forces, and I have my forces represented in sorry. I don't know what happened there. I have my forces represented in Cartesian coordinates. Right, so I'm going to form the equation of equilibrium. All right, put things together. Summation of forces is equal to 0. Forces are vectors. So summation of forces in x direction should be 0. Summation of forces in y direction should be 0. And summation of all the components of forces in z direction also should be 0 as a result of that. Maybe I should put some. There you go. So from the first one, what are the forces in x direction? The components of forces in x direction. What do we have there? These are all the forces we have. FA, TE, TD, and FD. Right? It's pretty much AX we have in x direction. And then we have TE, right? Exactly. So we had AX and we also have TE. We have these forces. This is one, another one, another one, another one. 4 forces. So looking at the I components, we can think about it this way. I components of all of them, we have AX plus TE magnitude is equal to 0. From the second one, what do we have in J direction in all these forces? AY plus TD, right? AY plus TD is equal to 0. And in Z direction, well, I have AZ following the same process, minus 200 is equal to 0. So from there, you can easily see you can find AZ immediately is 200 newtons. There you go. We found one component of the support force. Now, here we have 2 equations. How many unknowns? We have 4 unknowns. So mathematically speaking, we are unable to solve this. And we need more equations because we have too many unknowns. We need at least 2 more equations for 4 unknowns, right? As long as those equations do not introduce new unknowns. If they do, we should always have same number of equations and number of unknowns. So we'll go, we have more equations. We can actually form more equations, right? Aside from all the forces should be 0, we also know that summation or vector sum of all the moments should be 0 too. So I'll do summation of moment. Which point I have to take the moment about? Well, I don't have to. Which point is the easiest point? About point A. Exactly. Thank you, Sama. A is a vector. Why A? Because we have most number of unknown forces applied at point A. Well, in this case, it's not most because we already have AZ, so you could go with point B if you wanted to. Because right now we have AX and AY as unknown, and we also have TE and TD as unknown. So you could do either. You could either use point A or point B. Both of them have the same number of unknowns. But since I did A, I'm just going to go with A. I don't have a logical reason why I chose A. In this case, they're pretty much the same. All right, so if I do that, let's see what happens. Let's go with, all right, what we need to do is that we have to find the components or moments that each force in this free body diagram creates about point A. So what do I need to do that? What do I need to find that? I have the forces, or at least representation of forces in Cartesian coordinates. I have to find the vector connecting the point that is I'm finding the moment about to some point on the line of action of each force to find the moment of that force about that point. A specific force about the point I'm finding moment about. Very convoluted sentence, right? But the bottom line is, well, I need to know this, like the vector going from point A to some point on line of the action of this force FD to be able to find the moment of FD about point A. I'm going to call this, let's call this RC. I should have called that FC. Maybe it would have been more appropriate instead of FD. You know what? I just call this FD, FC. Since it's point C, it makes more sense to just call it. Let's call this FC and call this also FC. So RC is the vector for FC, vector pointing the distance from point A to the line of action of FC. All right. Next, the second point I'm interested in is point B. That's a point on the line of action of both force T and TD. So all I need to do is I have to find the vector RB. I'm going to try to put it here at the danger of things being a little overlapping. I'll call this RB. All right. So what I have to find would be, well, RB cross F, I would say, what they call it, TE. Let's go with TE. Plus RB cross TD plus, well, RC cross FC. This should be equal to 0. All right, so very similar to the previous example we went through. 3 is RB from point A to B or C to B. RB is from point A to B. All right. All right, that's what it should be at least. Because we're finding the moment about point A. So just the vector showing that point. All right. So 3 components, unless I made a mistake somewhere there. Let me double check. I get RB. Yeah, that should be correct. I don't know, Connor. You just asked that question. All right. Let me know if something is wrong there, but I think that's what it should be. So I have 3 components. Component 1, I'm going to calculate them separately. 2 and then 3. Just 3 cross product. Now to do that, obviously I have to find RB and RC. How do we do this? Well, remember that's where we usually start, but in this case we needed the we didn't need the coordinates or points. Now that we got into this point, we need those coordinates because it was easy to find the directions of the forces. So let's go with all the points that are important. Right, we have point A here. And we have point B, sorry. And here we have point C, or wherever the color is, I'll call it point C. So let's write the coordinates for these points, and from there we can find these vectors, position vectors. So a little easier to do that. You can just write it as is, but it's easier to just write the coordinates. So coordinate for point A. Point A is the origin. So it's just 0, 0, 0. Look at the coordinate system I took in my free body diagram. Right? This is my free body diagram. Where the coordinate system is, point A would be 0, 0, 0, because it's exactly at the origin. So that would be 0, 0, 0. Well, let's take a look at point B. Let's see where that is. What is the coordinate for point B? One, two. Well, look at the coordinate system. Well, it's actually two. Would be x is correct, 1. Exactly, 1, 2, minus 2. Yeah, almost there, but just sign. Pay attention that z-axis I got was upward. Right? So point B is 2 units down, 2 meters down. So that'll give us 1, 2, minus 2. I can write it better, minus 2. Minus 2. This confusing. Point C. How about coordinates of point C? How do we find that one? Right, this is where point C is. So if you want to trace it back to this axis, that one goes there, and that is pretty bad. And this one, let me use a color that is more obvious than this. It goes here. So it has some components on both axes, and then this goes there. We have to find this would be XC, this would be YC, this would be ZC. How do we find those? Would be 0.5, 1, minus 1. That is very exactly on point. Richard, can you unmute yourself and tell us how did you do that?
Since point B, like you can make a triangle, right? So the hypotenuse would be 3 meters, the length of rod AB, and the components are 2, or it's 1, 2, negative 2. So since C is like exactly half of the hypotenuse, then the other, I guess, sides of the triangle should also be a half.
Exactly. It's like two similar triangles, right? If we, thank you, Richard. So if we look at A, B, let me call this point some point like O. If you call this ABO, look at ABO as triangle in 3D space. Well, ABO, we have all the dimensions. Hypotenuse is 3, and the side, well, I would say adjacent is 2. So if you look at A, I call this O prime. AO prime C, well, hypotenuse is half the hypotenuse of the big triangle, 1.5. So adjacent would be half, and everything else would be half. So that's pretty much what he did. Let me see if I can actually draw it here. Maybe things get less if I can do a good job. And let's see, this is the triangle. This is the triangle that we have there, A, B, O, right? The triangle in the space, A, B, O. It's 3 and 2. This is 3 meters, and this is 2 meters. Go back, now I have ACO prime, all right? So let's draw that too. That would be exactly in the middle of this. Let me move things around the dimensions I put. So that would be I forgot how did I name them. AC is on this, and then O prime. AC O prime. If this is 3 meters and this is 2 meters, so this one would be 1.5 and this one would be 1. And that's how he or at least Richard, correct me if I'm wrong, but that's, I guess that was your line of thinking. So C becomes 0.5, 1 minus 1. Hopefully you see that in XYZ. Let me put that coordinate here. This is a coordinate. This is Y. This is X. And this is Z. I guess in this setup, well, yeah, that's correct. So two similar triangles, you look at the geometry, you'll get this is exactly in the middle point C. So it's going to be 1.5 and that's going to be 1. And then you can get this these values. So it's going to give you a 0.5x in X direction. Right, that would be making it mess there. So I don't know if I should add more. This would be 1. This would be so this is 0.5, this is 1, and this is 1. All right. So that's the tricky part, or maybe that's the most challenging part of this problem. Well, so it's just two similar triangles. Hypotenuse is half, or pretty much we can just find all the dimensions. Once I have the ones for the one, oh, in this case, the ones for the big one. All right. Now that I have the coordinates, should be easy, right? RB, I can write RB. Right? What is RB is pretty much just whatever is the coordinate of B, since RB is from A to B. So that would be I plus 2J minus 2K. Right? That would be my RB. RC, and now you see why I took the coordinate at point A, because it's the origin, so it's easy to find the position vector. Right? If you wanted to find, let's put it this way, if you wanted to find the moments about point B, it would have been easier if you put the coordinates at point B. So depending on where you put the coordinates, it actually makes sense to find the moments about a different point. If you had your coordinates at point B, you could just find the moments about point B, meaning that starting point for all the vectors, position vectors, would have been 0, 0, 0. Since I put it at point A, I'm finding a moment about point A. It's always easier to find a moment about where we have the most number of unknowns and where we have the origin of coordinate or coordinate system in most cases. They're not necessarily overlapping all the time, but if they are, great for us. So RC, or again from A to C, so that would be just 0.5 I plus J minus K. There you go. Now I have RB and RC. I can calculate every component of this moment. Right? RB cross TE plus RB cross TE plus RC cross FC. I have forces represented in Cartesian coordinates. I have position vectors represented in Cartesian coordinates. All I need to do is just find the cross products. Right? So one, I think it was RB cross TE. Correct me if I'm wrong, but I think that's one was RB cross TE. T just has one component, so just write it like this. We have I, J, and K. RB is 1, 2, minus 2. And TE only has component in I direction, so TE, 0 and 0. The rest is just finding the cross product. If you do that, you will actually get, this would be minus 2 TEJ, right? And then if I didn't make any mistake, minus 2 TEK, I believe so. Let me double check. Nothing for I, minus 2 TEJ for K. Yep. All right. The second one was R, I believe it was R BTD, right? And TD has just a component in J direction. So RB cross TD. I, j, k. RB, I found it as 1, 2, minus 2. And then TD is just, it has one component, the magnitude in this direction. This one gives you, I think, 2 TDI plus TDK. Yep, all right. Third component, it was RCFC, right? RC cross FC. So I, J, K, RC is 0.5, 1 minus 1, and FC only had component in Z direction, if I'm not wrong, so it was 0, 0, minus 200. Do this one, minus 200 I, and then plus 100 J. All right. So now we have all the components represented in Cartesian coordinates. Right? We found what we were trying to find was summation of moments about point A. We said it should be equal to 0. Now I have the components, so I just sum up components and write them based on their direction. Right? It's X, Y, or Z direction. You can write it all together and separate them. I'll just write whatever components. Let's write I component, J component, and K component in X, Y, Z direction. In I direction, you get 2 TD minus 200 is equal to 0. In J direction, you get minus 2 TE plus 100 is equal to 0. Also, you get something in K direction. You get minus 2, if I'm not wrong. You don't even need to write that. Minus T, 2 TE, sake of completeness, plus TD, if I didn't make any mistake, should be this. So from the first one, you can just get TD, right? 200 divided by 2 is 100 newtons. From the second one, you will get TE, 100 divided by 2, 50. Right? So there you go. We got the tension in D and we got the tension in cable E. So what were we looking for? Don't get lost. We were trying to find the tension in cables BD and BE, which we found. And we were supposed to find the reactions in ball and socket joint. We found one component of reaction from before. It was AZ here. We couldn't find AX and AY, but now AX and AY is two equations and two unknowns. We got rid of two unknowns because we already now know TE and TD. So all I need to do is just to follow this. Let me put this star so we can follow this later. And as much as I hate doing this, but let me just separate this part. So from star, you get AX is equal to and AY is equal to, AX would be, I think, TE minus TE, and that one would be minus TD. So because minus 50 newtons and minus 100 newtons. So that would be your AX, that would be your AY. Now, obviously, these minus signs, what they're trying to tell us, they're trying to tell us that, well, the magnitude is correct, but the direction you assumed on your free body diagram is not correct and it should be flipped. So if I wanted to draw this free body diagram correctly, and if I knew the correct direction, I should flip AX and AY. So instead of going in the positive direction of X and Y axis, they should go in negative direction of X and Y axis. And as we said before, generally speaking, that's why it doesn't matter what specific direction you assume, because at the end, if your direction is incorrect, you get the correct magnitude but the wrong sign. Just keep in mind that you can't make the wrong assumption about the direction of the forces when it comes to cables and chains and ropes, because they're always on tension, under tension. So direction of T and TD, you should be able to put it in the correctly. Direction of components for AG A or the support reactions, that's fine because we don't really know. It can be in either direction.